Thank you, Benny. So, you guys good with what we said earlier? So we explained some generalities about the spectrum, and we discussed that the graviton is always there, right? And that in weakly coupled string theory, the dilaton is always there, right? So first of all, I wanna fix this thing, and then yes, okay. And now I wanna tell you what the role of the dilaton is, because these are states. Remember, the first word is states, the second word is dynamics. So where's the dynamics? Well, I wrote this path integral. It's pretty cute, but what if I want to actually develop it some more? Well, let's develop it some more. So dynamics. So I told you in the beginning that in gravity, in asymptotically flat super selection sectors of quantum gravity, it seems like the S matrix is the only meaningful observable. There's nothing else. Like perturbatively, you may define correlators or whatever, but non-perturbatively, there is nothing else. Now, how does the string theory tell us that this is the case? In fact, like even if we didn't know this, string theory would force us to realize it. So yeah, we see it from basically that construction. So that's the generic path integral for any quantity we wanna discuss. Basically, in here we put a bunch of things. So I'm going to discuss this, the meaning of this soon enough. It's like some transformations that you cannot gauge fix away. They will play a somewhat important role in the calculation. But so how does one actually construct a more explicit path integral of that kind? Well, so as I said, the dilaton, the scalar field, the dilaton is always present, and it's also part of the generic background of the space-time sector of the worldsheet. And what can we do with scalar fields? Well, in asymptotically flat space-time, there's always one thing we can do with scalar fields, which is giving them a constant background value. They could have non-constant background values, but at least the constant one is always available. And it's the value at infinity, let's say. And then we could have like fluctuations around it. Now, what does this decomposition buy us? It buys us that the part of the Polyakov action that describes the dilaton, remember, is something like 1 over 4 pi, alpha prime, it cancels. And then we have our, well, let me give the Euclidean version directly, gauge fixed metric. Then we have the Ricci scalar of the worldsheet. And then we have our little phi, right? Now, the neat fact about this term, I mean, this term is stupid. Like it's same as before. It's an interaction term. It's complicated on the worldsheet. This term is cool because this is a constant. And then you know what this is? If this is the worldsheet, this thing is the Euler characteristic of the surface. Gauss-Bonnet theorem in 2 dimensions. Pretty cool. So basically, this thing contains a term which is phi 0 Euler character. And in particular, for those worldsheets over there with like a number of holes given by the genus G, this is sigma G. This is phi 0, 2 minus 2G. For more complicated Riemann surfaces with boundaries, cross caps, and so on, it's more complicated, but doesn't matter for us now. So this is the formula. This means that in the path integral, so in the path integral, we have sum over genera, and then there's a prefactor e to the minus s, right? Which has like e to the minus this. Now, let me creatively call e to the phi 0 gs. And now this is the meaning of the GS that I wrote at some point earlier. This is a constant, it's a positive constant, and it appears in the path integral like so. And now I have my moduli space integrals, you know, there's some measure that is determined by the Fadeev Popov procedure. It's complicated, but you can do it. Details in Polchinski. You thought I was gonna say in the notes. I mean, some details are in the notes though. And then there is the integral over the worldsheet theory. So I'm just gonna call this a connected correlator in the worldsheet theory with some genus G at some moduli over which I integrate. Like for instance, if it's a torus, I can deform the torus in various ways. The inequivalent tori are given by this moduli space, or super moduli space for superstrings. And then here, I finally know what I can put. Vertex operators for states. And I have to put the gauge invariant ones, which means that I don't get to compute space-time correlators. They don't exist. There's no such thing. Even at the perturbative level, string theory tells us that there is no such thing. The only thing you can compute is S matrix amplitudes, because here you have to put vertex operators, integrated, unintegrated. We said it's basically the same thing for states. These are states. So they can have like polarizations and they can have momenta, right? States. And there's some normalization that is fixed by unitarity. And this thing is just the asymptotic series, perturbative asymptotic series for our S matrix. Up to the little details that I'm not putting, but that's the structure of it. Right? Pretty cool. So this is how we build interactions, and this is how the string coupling comes. And now you see explicitly that it was never a free parameter. It's just a background. It's part of the background, right? Any perturbative theory, you expand around some background. Then there's the background data, and then there's the free parameters. In string theory, there is no free parameters, only the background data for the perturbative expansion. But of course, the theory is doesn't have the parameters to begin with. Okay, cool. So what can we do with this object? Well, we can finally do some low energy physics and some high energy physics. So let's start. Let's start with low energy physics. I would say it's less of a dramatic departure from what you know. Yes. No. Yes, it's a real valued yes, because it's the value at infinity of a scalar field in an asymptotically flat spacetime. So it can be any real value. It's part of the background, so it's not a parameter of the theory. It's a solution to the equations of the theory. Yes, yes. Like if you can pick it freely, say there's no potential with some minimum, which is the case in what we're considering, it's a modulus. It's not a parameter. It says, okay, it's part of the space of solutions. Cool. Great. All right. So how do we do low energy physics? Low energy strings. Well, basically what we can do is we can take that and we can compute. So there are a couple of ways of doing this. So one way, like let's say we discuss two ways of doing this. One is we compute these S matrix for massless states. Because in the cases we're considering here, these are the only ones that are not new physics. They're the ones on the left that are below the cutoff, right? In this very simple case, these are the only ones. Otherwise, one can concoct situations in which there are massive states which are still light relative to cutoff, but it's not the case here. In the very simple cases we're considering. So we do this, and then we can expand. It can expand in the, let's say, infrared regime. For example, in a 2 to 2 scattering, 2 to 2 scattering, this will be something like 2 pi, I mean, ignoring the identity part, there's gonna be some delta, blah, blah, sum over momentum, conservation. And then there's gonna be the reduced amplitude as a function of STU, and perhaps the polarization, like there's gonna be some kinematic factor with the polarization, let's say, something like that. And we can expand this for STU much less than the UV cutoff, which in our case, it's just the string scale, right? And what we get is a bunch of terms, the first of which will match with like Einstein gravity coupled to matter, and the rest will give us higher derivative corrections. So this is something we can do. The second thing we can do, so this is the coolest approach because first of all, it uses the observables. And second, in principle, it gives us all the higher derivative corrections for all possible sectors of the theory and all loop corrections as well, right? All the quantum effects, right? The string effects and the quantum effects for all possible states. Then there's a more restricted approach, which is, more convenient. It's easier in some sense, but it's also good to mention, not just because it's practical, but also because it's conceptually connected to the initial story, namely the fact that the background and the states are not really separate things. You can go from one to the other. You can deform the background by coherent states and so on, like I explained before. So it's important that an approach based on states be equivalent to an approach based on the background, right? So what is this approach? Background consistency. So this is an approach that is valid also in the world line. Let me mention this. You can observe that not all backgrounds are okay, but this we already knew. Not all CFTs are okay. They have to be modular invariant. They have to be critical and all that. But when saying this, I basically ignored the spacetime part. I said, yeah, the leading order is fine. It's just flat spacetime, whatever. It's fine. That's true. But what about subleading terms? Right? Even if spacetime is weakly curved, like even if the curvatures in string units, well, let me say calligraphic curvatures of all fields are small, there are still corrections to the central charge criticality conditions. Namely, we have the leading part, which we already examined yesterday. So this part must vanish by itself, and this is the criticality condition. And then there will be some other guys, other terms, right? In this asymptotic expansion. And again, they have to vanish order by order. There's no escape, right? And this vanishing leads to some equations. Like the background curvatures need to satisfy some equations, right? Which is basically the condition that this vanish order by order. And now it is much simpler to, I mean, you see that the worksheet CFT by itself describes a single string, right? Which means that this condition can only be valid at tree level in string perturbation theory. So at tree level not in alpha prime, but in GS. So you see we have a double expansion in curvatures, tameness, and weak coupling, which is the GS expansion there. Two expansions. One was motivated by the gravitational instanton story, and the other one by observations, by the fact that we see a weakly curved spacetime mostly. Also, it's convenient. So we have these two expansions, and this method can only work at tree level in GS. And moreover, let's say up to sophisticated formalisms that are not this RNS formalism I've been using. Here we are confined to the NSNS sector. You see, I gave you the various possible sectors, right? Basically just here for the background fields G, B, and phi. But this is what we care about, so it's okay. Like to prove that there's general relativity, this is enough. Coupled to other stuff, of course. So these are the two approaches that we could follow. Right? And again, let me stress, this approach is also true in the world line. There's nothing here that says stringy, even though you could say, oh, but wait, the Weyl invariance you told me was something stringy. Yes, that's true. But this particular condition also follows from the BRST cohomology condition on physical states on the world line. The difference is that with the world line, you get the, like, for instance, Einstein's equations. That's it. From the worksheet, you get the curvature corrections, the DFT, the all order corrections in principle. Right? Cool. So both of these approaches lead to the EFT description of the low energy, I mean, the low energy dynamics. Right? Does that make sense? Cool, because I gotta run. Um, okay. So let's start with this actually, because you see, this basically gives us the EFT, and that's pretty much it. This is the actual observable, and it gives us the EFT, low energy stuff, but also the high energy stuff. So that's yeah. You mean like membranes and stuff? Yes, of course.
So the same type of higher derivative corrections or more?
Well, structurally is the same type, but the weights are different because, like, for example, so already also the EFT level, you can see these objects as solitons. So like agglomerates of energy density of fields. And then from the worksheet picture, you can see them as like boundary states. You can see these things. These solitons, um, basically, they can produce higher derivative terms in certain settings. And most prominently, when you don't have like coupling between Bloch and boundaries of these guys, you can have instantons of this type, like D-brane instantons or worksheet instantons or things like that. Well, the worksheet instantons are a bit different, but the point is that these guys will contribute higher derivative terms weighed by like non-perturbative weights, not just perturbative weights. So yeah, they're there, yes. And actually there are ways to compute these things exactly through string dualities. And so there is an example that I kind of wanted to mention, not explicitly, but where you can actually explicitly see the presence of like these D-brane instanton terms in the higher derivative expansion. Yes. So all of this was already started, I mean, in the 90s. Like people were doing this stuff in the 90s already. Yeah. Pretty cool stuff. Okay. So yes, so let's start from this because it's sort of limited, but also it's more explicit in this way. So how does this work? Well, we gotta make sure that at least, let me just give you the first subleading order, that the background be consistent, namely free of anomalies, in particular free of the Weyl anomaly, right? So what do we do? Well, first of all, we said that the theory must be conformal. Like once you gauge fix away everything, the leftover worksheet theory and flat worksheet must be conformal invariant. And now you know from the previous lectures that the beta functions must vanish, right? So let's write some beta functions. So there are beta functions or beta functionals, to be more precise, for these couplings, because these couplings are functions, beta functionals. So there are some betas like this. Right? Now, this doesn't actually appear in a flat worksheet, but you can compute it on a curved worksheet if you want. And you can compute them, again, let's say, asymptotically to leading order in this expansion. Now, what is this expansion? Well, this means, for these particular fields, it means that the Riemann curvature, right, in, let's say, the whole tensor be much smaller than alpha prime, but also the H curvature, remember the three-form curvature of the two-form Kalb-Ramond field, and also the scalar curvature, right? So these guys have to be small in string units. Okay, so what do we get here? So up to prefactors, what you get is the Ricci tensor of the thing. So, oh, by the way, you can compute this easily using for example, the heat kernel. The heat kernel technique that was explained by previous lecturers very nicely. And in particular, this is a 2D theory where you use the heat kernel, so it's much easier to do. And I know because even I can do it. And what you get is something like this. Let's say mu nu rho. Sorry, no. Mu rho sigma, nu rho sigma, something like that. And then here you get something like this. And here you get, yes, it's this. So this is the Laplacian, right? Space-time Laplacian. So these are the actual beta functions. Now, the theory must be conformally invariant on a flat worldsheet, but it must the conformal invariance is not the same thing as Weyl invariance when coupled to gravity. So the Weyl anomaly, this thing, actually gives you other terms in these beta functions. So these are the actual RG beta functions, but there are other terms. So these are the Weyl anomaly beta functions that you get if you actually compute the Weyl anomaly. And they have an extra term. So this extra term looks like this. No surprise, they involve the dilaton, because the dilaton is the guy that couples to the worldsheet Ricci scalar, which is the extra dynamical degree of freedom of worldsheet supergravity, right? Well, together with the Gravitino, which I'm not putting here, but you can find the supersymmetric version of this in a review by Callan and someone else. Yes, Torlacius. I mean, these are you get the same result in any scheme. You can use the auxiliary the functional K scale. You can use the Polchinski lambda. You can use the perturbative mu. Anything gives you this. Yes. So yeah, and then you get and here you get this, and here what was it? Yeah, I think you get something like this. Yeah, should be correct. So maybe I can just double check. Right. So these ones, the Weyl anomaly beta functions are the coefficients of the independent pieces of the Weyl anomaly. Now I didn't explain. Right, that's what I was gonna say. Yeah. So what is the quantity that detects the Weyl anomaly? So the Weyl anomaly, remember, is where do I write it? Yes. So the Weyl anomaly is an anomaly in Weyl transformations, which are transformations like, you map this into something like function of the worldsheet. Like it's a rescaling, smooth rescaling of the worldsheet metric. It's a gauge redundancy. So you can compute, for instance, the variation under such a transformation of let's say, the connected generating functional, for example, as a function of the worldsheet metric, right? Before integrating over the metrics, of course, because you got to make sure that the theory is anomaly free first. And you can evaluate it here if you want, but you don't have to. The point is, so that let's not do that. You get something which is actually the vev of the trace of the stress tensor of the worldsheet. It's kind of simple to see because the variation of log z with respect to the worldsheet metric is the worldsheet stress tensor, but the vev of. Otherwise, you vary the classical action of the quantum action. And the fact that it's the trace, you see, because what you're varying is the overall prefactor of the metric, not the whole metric. So you get the trace of T. And this thing will have, in general, three pieces, which are the three pieces in the Polyakov action. Like you get something times like dx dx, then you get something times, so this is gamma dx dx, and then epsilon dx dx. So this is related to the B field, this is related to the metric of spacetime, and then you get like something with the Ricci scalar. And this is related to the dilaton. And this is how you compute these. Now, when you kill the first two, you get only this, right? And this is supposed to be, actually it must be, this coefficient, it must be proportional to the central charge. Remember, the total central charge. It becomes the CL plus CR, the C, let's say, total of the sorry?
D minus 10.
Proportional to D minus 10 in flat space-time, otherwise there are these corrections. Yes, yes, exactly. And it must be a constant, right? And that constant is C minus the critical value, which must vanish by volume invariance, yes, because otherwise there is an anomaly indeed. And the fact that this must be the central charge follows from general considerations on CFT. But the fact that if you kill these terms, this becomes a constant, it has to, right? Otherwise conformal symmetry doesn't work. This fact is true to all orders because of the so-called Curci-Paffuti relations. And I want to mention this because Paffuti was my quantum mechanics professor, and he passed away a few years ago, so I wanted to sort of pay some sort of tribute. Yeah. So this is sort of thank you for asking. So the point is to kill these guys, of course, plus all the corrections, and it can be shown that again to all orders, this thing, these are three equations for fields. They do follow from an effective action. Like there is an action functional whose Euler-Lagrange field equations give you this plus the corrections. And this gives us the effective action of the NS and S sector at 3 level in string perturbation theory. And of course, we also keep the leading order in the alpha prime expansion here. And again, the very first term Z appear also in the word line formalism. Here we get all the corrections too, which ultimately encode Wilson coefficients from the UV completion. Right? I'm gonna mention one of these, but I really gotta speed up, I think. Oh, no, actually I'm pretty good on time. Okay, so dimensionally there must be something here, and the only scale in the game was ms. There must be ms to the d minus 2. And then there's like our thing here. I'm going Lorentzian for the purposes of space-time physics here. And then the natural way that the action presents itself in these variables is this. Right. So it's essentially Einstein gravity coupled to matter. Now, for those of you who know about the Jordan frame in scalar tensor theories or stuff like that, this is called the string frame. It's a special case of what you may call Jordan frame. You can go to the Einstein frame where there's no prefactor here. And if you do, this fixes this factor here, actually gives you the proper sign. Because you may say, oh, this is not the right sign for a scalar field kinetic. It is after you go to the Einstein frame. So everything is fine. And then it introduces a coupling here between these two also. So I'm not gonna do that, but in order to do that, you gotta separate the zero mode first, the GS term. And if you do that, you see that this contains a term GS to the minus 2. And then you have your fluctuating field, which you can reabsorb in the Einstein frame. Einstein frame meaning that the action starts with R. Yes. Whether they are ghosts or not doesn't depend on this. It's just a way to present the action. Yeah, I know. This sign is correct. Because once you canonically normalize the field, it's fine. So this factor here is the one that governs our interactions, right? So because there's only this thing that governs our interactions, you may expect that whatever Newton constant appears will be proportional to some power of GS. That's indeed the case because you see, this goes here in front of the integral. At the end of the day, once you do your Einstein frame shenanigans, you end up with m Planck d minus 2, which is by definition the coefficient of the Ricci scalar. No? And if you do the little math here, you get ms d minus 2 over gs squared. So what we just saw is that the Planck scale exists, like it's finite. It's not like so. It tells us that the leading order term in the gravitational sector of the EFT is actually Einstein gravity. It's not like R squared or Weil gravity or whatever. Right? It's actually bona fide Einstein gravity. And this is the Planck scale relative to the string scale. Right? And you can see that in the weak coupling limit, this is what I was promising you. Like you see that ms is much less than m Planck. And moreover, you saw from here that in this very simple case where without other additional scales from the internal degrees of freedom, you can assume that everything is ms sized. The higher derivative corrections are weighed by a cutoff, which is ms. So you see, this is a weakly coupled quantum gravity theory under the definition that I gave yesterday. Everything fits together perfectly. And okay, this is great. Well, as I said, this is part of the story. The full story is in the S matrix. And OMG, I have to close the parenthesis here, otherwise I go crazy. Okay, cool. Any questions?
String coupling is universal, right?
Define what do you mean by universe?
It doesn't the excitation.
No, it's part of the background,
Yes,
the background data.
but then if we have different excitation states that correspond to different particles, then they all have the same string coupling.
That's right. That's right.
Because different particles don't all have the same coupling.
So what happens is that if you go to this EFT description where you can actually extract the couplings between the things, they will be functions of GS. They will be determined by GS. They need not be the same power law. Okay, good. The point is that there are no free parameters and everything is determined by the background. Okay, good. Thanks. And of course, you see by the various invariances, diff invariants and so on that we get in this theory, every time GS appears, it must appear together with delta phi in such a way as to reconstruct the full phi, because the split was just a choice. Everything must coalesce back into the full dilaton in the end. It must, and it does. Good. So this is the leading order EFT. Now, maybe, yeah, actually, this is a great place to start. So we can use the S matrix to reproduce the same result, and also all the other massless states or light states, if any, to all loops, etc., etc. Let me give you an example. So let's compute something. Let's compute something that pertains to whatever comes after. Am I okay on time? Okay. What? Okay, well, I heard 5 minutes. I was like, what? Okay. Let's compute something. So this is the very leadingest order. But again, the theory can tell us more. So we just recovered GR plus other stuff. Great. But we can do more. For example, what is the simplest thing we can compute here? The simplest test amplitude. Well, the ones that make sense. So no tachyons allowed. No tachyons in this bar. You know the jokes about tachyons, like The tachyon exits the bar, the tachyon orders a beer, and the tachyon enters the bar. Yeah. So what's the simplest? The simplest thing. The simplest is just like 2 to 2 graviton scattering. I like gravitons, sue me. 3 level. This is pretty much the simplest thing we can do. And I promised I would show this, so I am. So this is the case, and this will give us what's called the Virasoro-Shapiro amplitude, which again was one of the OG amplitudes that was like presented before the theory really came into its own, together with the Veneziano amplitude in the late 60s. So not exactly Gen Z kind of material. Okay.
I said easier than the left good.
It's not, but I said I like gravitons. It's as easy. It's not. It's not. Okay. You get it. It's as easy as. Okay. So how does this work? Um, how does this work? Well, so first of all, G equals 0 is the 3 level, right? Which means that we get. Well, let's see here. So let me do this Virasoro-Shapiro calculation. Well, sketch it. What are the details? In the notes. And in Polchinski. So the details in the notes are the sketch of the calculation and the references to the actual full calculation. Anyway, yes, so we get a factor of GS to the -2, right? G equals 0. Then I told you that the actual correct normalization of these guys is GS per vertex operator, and we have 4 of them, 2 to 2 scattering. So we have actually GS to the +2 in the end. And this is cool because you see, this is just 1 over 8 pi g Newton, which means that GS squared is basically g Newton in string units. And because we're computing everything in string units, right? In the end, it will come as g Newton in front, which is exactly what you expect from a 3-level gravitational amplitude. Pretty cool. Okay, so there's that. Let me just say GS squared. Then what do we have? Well, we have the correlator of 4 vertex operators of gravitons on the sphere, right? Now the sphere has no moduli actually, but this is not just a sphere, it's a sphere with 4 insertions. So this is a worksheet that looks like this, because this is conformally equivalent to the diagram I drew there. It's like 4 tubes that stretch like so to infinity, giving us the asymptotic states, right? If I think you can picture this, right? You guys are good at this kind of stuff. I mean, we do this for a living. Okay, so we get this stuff, and what do these guys look like? Well, these guys look like, and here come the punctures. They are integrated vertex operators. So we get actually 4 integrals over the worksheet positions where we insert these guys. But here comes the residual symmetry that I was telling you about. It's you see, it's something. This is why I left the space. It comes from the fact that the diff times while, or the supersymmetric counterparts thereof, can be sort of divided in pieces. You can take out these small differs, right? This is these small differs. And this gives us the mapping class group that gives us the moduli space. But here there are no moduli, so forget about it. In here, after gauge fixing, there's something left, which is the conformal group, the group of conformal killing vectors, right? That leave the Lie derivative of the metric under these vector fields is the multiple of the metric. It's a scalar multiple of the metric. So these are the conformal killing vectors. And the sphere happens to have, well, depends how you count, either 3 or 6, right? If you count 6, it's like the real counting. And here you have how many, like you can use this freedom to basically shift the positions of these insertions in such a way that you can kill these integrals, basically, because they are redundant. And so, you know, the sphere has dimension 2, where sheet is a surface. So 2, 2, 2, 2, and the conformal killing vectors are 2 plus 2 plus 2. So you can kill up to 3 of these insertions, and you can fix them wherever you want on the sphere. So for instance, if you, I think you're familiar with the Riemann sphere, right? The sphere seen as a Riemann surface with a complex coordinate. You can fix these guys to 0, 1 as a complex number, and then complex infinity. These are very convenient points. And then the last point you keep. You can call this like, you know, sigma 0, infinity, or whatever. You can use any coordinates you want, but the result will be the same, right? Cool. So how does this calculation work? Well, I mean, you may be worried about this, but it drops out of everything because of Weyl invariance, and actually momentum conservation follows from this. So you don't need to worry. You can just forget about this. This will never appear in the calculation, basically. Good. That's why it's convenient to gauge fix it there. Again, details in the notes. And right, so we kill these 3 integrals, and what we're left with is a correlator of 4 things integrated over the last guy, or yes, the last guy. Now these are correlators in some worksheet CFT, so a 2-dimensional theory. And again, let's say we want the simplest case, the simplest background. So I forgot to say, but the simplest case, of course, is flat space, right? Flat space time. Flat, so G equals eta. That's the simplest thing, and that's the actual Virasoro-Shapiro amplitude. So in this case, of course, it means that B is also 0 because of the isometries of flat space-time. In this case, the worksheet theory, the Polyakov action there, is a free theory, just a free theory. So these are correlators in a 2-dimensional theory that looks like this. Once you gauge fix to the flat worksheet, you just get dx dot dx plus fermions. So it's free fermions, like the phi d slash phi, psi d slash psi. That's it. It's a free theory. Now the correlators of a free theory of vertex operators corresponding to external states in space-time gives us the space-time S matrix. And it's a very convoluted way of doing things, but it works analogously in the word line approach. Right? The MVPs here are like Weyl invariants and all of that. And the fact that it's a 2-dimensional theory, not a 1-dimensional theory. So it's not such a dramatic departure from QFT. It only appears to be because in QFT we can be used to like a space-time Lagrangian description when available. Right? But here we can't do that. So what does this look like? So let's maybe move on here. So we compute this thing, and then we use it to go to look at the Wilson coefficient, compare it with like bootstrap bounds, and then the high energy physics, and then we skedaddle. So what does this V look like? Well, schematically, let me put a little arrow here. Remember the structure. There was the momentum, space-time momentum bit, and then there are some things here. Again, forgetting about ghosts and superghosts, there are stuff like dx.dx in the bosonic case, or psi dot psi. Well, not dot. I mean, there are some polarizations here. In the RNS case, or psi dx in in the heterotic case, right? And then there are some subtleties. I mean, you can recast these operators in a different way using what's called the picture changing operators. It's complicated, but the basic structure doesn't change. What matters is that you have this combinatorial structure. You have like these polarizations, and this is important. So this is what makes the calculation annoying, but also this is what makes it skippable, because I can tell you how this affects the result. So I focus on this bit, which would be tachyonic without this. So this actually produces the original Virasoro-Shapiro amplitude, the one for tachyons. And then I tell you how this changes the result and why, roughly. So we focus on these guys. So we need to do something like this. P1.x of 0, P2.x of, let me just call them for now sigma 1, sigma 2, sigma 3, and sigma 4, right? For the free theory. Now, free theories give you Gaussian path integrals. You know how to do Gaussian integrals, right? Like the action can be written basically as, the action has this schematic structure. Well, let's say we only care about this. So let's say we have this integral, dx dot dx. We can use the very convenient notation that Benjamin used to write this after integration, etc. Basically, we write it as like x times some kinetic operator times x, or with a little circle if you want. Now, this operator is basically the box and has 0 modes, right? Because we can move the center of mass of the string wherever we want. So the path integral is also over the 0 modes. And it's convenient to separate them. So if you separate them, x is like, let's say, lil x. And remember, this is a mu index plus y. And this is the actual field. Well, the non-zero mode. If you do that, this will not, I mean, the 0 modes, you see that this only contains y, right? So only y appears in the actual action that you integrate with Euclidean action. Alrighty. So what happens here then in the correlator? What happens is that we get the 0 mode bit is always the same, doesn't depend on position by definition. And it just goes out. And there is a path integral over the 0 mode, which is just a normal integral. It's dd little x e to the I, well, sum over the momenta times x, little x, right? And then there's the rest of the correlator, like the product of these. Right? Makes sense? Lo and behold, this is the momentum conserving delta function. It just comes out, and it kind of had to, because of the space-time isometries. There was no other choice, right? Had to come out. And this will give us something proportional to the reduced amplitude whose prefactor is fixed by unitarity. Right? So what is this? Well, we can compute this. You see, we get something like e to the minus y circle k circle y, the Gaussian piece, by using the condensed notation of Benjamin. And then we have like plus I, and then a bunch of momenta, like this is I to the e to the I sum of these guys. Now, we like our fields to be integrated over, not localized a bit. So we can just write this in terms of e to the I, and then we write sum over k, ek, delta for sheet, sigma minus sigma k, and then we integrate over the worksheet, right? So we just do like, right? And this is like J circle Y, where J is this. It's a source. So we can just do j dot y. And you know how to compute this kind of stuff. Like I'm just gonna, skip the details. You must complete the square and do the usual kind of stuff. I mean, of course, here there's a 1 over 4 pi alpha prime in standard coordinates, not in complex coordinates. And okay, so if you do that, you can sort of expect the result already. Like if you do this path integral, the path integral with a source will give you, again, this should be very familiar to all of you, but it give you like gives you e to the j propagator j. Now the propagator on the worldsheet is basically free propagator of a scalar field in 2 dimensions, times like the identity of of a bunch of scalars in this case. So g of sigma minus sigma prime is proportional to just log of the distance. So let me call these sigma 1, sigma 2. Let me call sigma 1, 2 the distance, Euclidean distance. This is the propagator in 2 dimensions. It's the Coulomb potential in 2D electrostatics, right? If you will. And the analogy with electrostatics goes further, actually, both in CFT and in string theory. Therefore, you see, we get like sum over I, sum over j, p I, pj, and then a log, like some structure like this. You get e to the, and then if you keep track of the factors, there are some alpha primes around. You get something like there's some prime over 2 ij ei dot pj log sigma ij. Right? So, you can just symmetrize the sum to get rid of this 2. Of course, this is always like the different guys. And then you get just the product over I less than j. You get this because the correlator is connected with. And you get like sigma ij to the alpha prime pi dot pj. So this is the integrand of the amplitude. It's a CFT correlator, nothing fancy, but it's cool because it basically appears universally in these like flat space correlators flat space amplitudes. It's called the Koba-Nielsen factor. So you will find this name, Koba-Nielsen. And it's at the foundation of like many properties of string amplitudes, including the high energy behavior that we're talking about, and the relations between open string and closed string amplitudes called the KLT relations. It's a whole thing. Details in the notes. Okay. So we have this chunky boy to put in here. Now this is this part. This is the Koba-Nielsen factor. Okay. Good. Now we just do the integral. Oh, wait, not yet. Not yet, because the vertex operators have these additional guys. Now, I can sort of sketch what happens. What happens is that in order to get these pieces from the Gaussian integral formalism with a source, you have to add like other pieces to the source. You differentiate with respect to the source, you get some factors down, and then you differentiate with respect to those positions, and then you set the positions equal to whatever they are. So it's a straightforward procedure, nothing conceptually new that you have never seen before. But you see, if you do that, you basically get some propagators down when you differentiate with respect to sources. And then you have to differentiate twice because, like, for example, here, you get like tan. For the fermions, you don't have the derivatives, but the propagators are different anyway. So in the end, you get like twice the differentiated log sigma, which is 1 over sigma squared. So 1 over sigma squared means that this exponent is shifted by -2. That's what you get. And then, of course, I mean, there's more to this. There are polarizations and etc. that give you the kinematic factor in front, the one that we have never rendered explicit because we don't really care about it. So in the end, it doesn't even matter. No, in the end, in the end, what you get is an integral, well, gs squared, kinematic prefactor, then integral over our worldsheet. And then there's this Koba-Nielsen factor, but you see, there's basically only two pieces. Like there's this with this and this with this. Because the distance between 1 and 0 is 1, and 1 to any power is just 1, it drops out. This bit factorizes away, it doesn't matter. So we only get two terms, sigma and 0 and sigma and 1. So we basically get sigma, well, the unfortunate choice on notation. Let me just do this. Like we get the distance between sigma and 1 and the distance between sigma and 0. And there are like alpha prime, P1 times P4, right? P1 times P4. Now alpha prime P2 times P4, right? Minus 2, minus 2. Cool? All right. Now, we can further constrain, well, you can further express these as like minus alpha prime T over 2 minus 2 and minus alpha prime U over 2 minus 2, the Mandelstam variables, like all of these. You can do some relativistic kinematics to express them in terms of Mandelstam variables. Yes. So the question is whether all the previous calculations ended up in the Koba-Nielsen factor. Yes. The delta function for momentum conservation and the Koba-Nielsen factor. And now we add the extra polarization effects, and we get the kinematic prefactor and the shift in the exponent right here. And then it's just a matter of doing the integral, and there are some techniques like Schwinger parameterizations, Gaussian integrals pop up. It's a textbook matter to show that this results in like a prefactor like 2 pi. And then finally, you get gamma, well, you get, let's say, what matters to us is like gs squared, let's say g Newton, up to scales. Then you get the STU of GR. And then you get 1 minus alpha prime S over 4, 1 minus alpha prime T over 4, 1 minus alpha prime U over 4. Remember, S plus T plus U equals 0 for gravitons because it's a multiple of m squared for identical particles. And then you get the same thing with a plus. It's a crossing symmetric result as you expect. And there you go. This is the graviton amplitude, the 2 3-level graviton amplitude in a flat background. Okay. So you see that basically you get GR plus something that when SPU are much less than ms squared, which is just 1 over alpha prime, right? You get 1, which is the GR result, plus corrections in powers of STU. Of course, if you computed the loop terms, you would also get logs and non-analytic pieces. So everything checks out. And no one is smiling. Okay. So, but it's pretty cool, right? And there is a detailed expansion of this in the notes. It was done by Green, Van Hoven, and, well, others. And the very first correction, what is the very first correction? The very first correction is, well, where can I, maybe there, that's already there. Actually, here, there's a bunch of space connected to the same topic. So the first correction in the IR, of course. What is it? So the term is like 1 over STU up to the kinematic prefactor. And then there's something else. Dimension minus 6. So it's some constant, alpha 3 level. Let's say string frame, because you can get the Einstein frame version, times ms to the minus 6. And then this is a constant term, and then there are powers of STU. This thing is, I believe, is something like this, like it's proportional to 2 zeta of 3. I think in the right units, let's say it's 2 zeta of 3 in this units up to a prefactor. So the point is that it's a zeta value. You can compute it by expanding this. So what is this coefficient? It's the prefactor of a constant. Which operator in the effective field theory gives you a constant in graviton scattering? Well, it must contain like 4 bits of gravitons, and it must be a higher derivative correction. It's basically a Riemann to the 4 contraction. The precise contraction is given in the references, but the point is that it is a Riemann to the 4. It's a purely gravitational higher derivative operator, and so you get this kind of action. Of course, so this is the Wilson coefficient that predicts at 3 level. Of course, at 3 level, there will be like 1 over GS squared in string frame. So actually, there will be like a e to the minus 2 phi, if you will. So this is the Wilson coefficient at 3 level. And yeah, good. Then
Expect like, I mean, naively, I would expect
right. Well, no, but R squared is not there. It is the this is independent of SUSY actually. This was derived in. Sorry, what's the question again? Like it doesn't show up in supersymmetric cases. Yes, I agree. But it also doesn't show up in string theory regardless of supersymmetry.
You cannot have square or cube in the type 2B.
Exactly. But what I'm in that case, yes, you can anticipate it. What I'm saying is that this is actually independent of whether it's supersymmetric or not, because 3 level amplitudes don't even care about the dimension. So you see, I'm not doing 10D. I'm doing D less than or equal to 10. This result is independent of that.
Easy calculation that you get.
Indeed.
You ask, why don't you have something smaller than R cubed?
Exactly. So the reason is R squared cannot contribute to 3 level graviton scattering because of the usual story. Now, Riemann cubed would have contributed something that is like 1 over S plus 1 over T plus 1 over U. Just happens not to do it. Not sure if in the yes, because there are other. Well, okay. Actually, let me put it this way. So the Riemann cubed can show up in other amplitudes. In fact, also R squared terms in certain heterotic theories do appear, but they show up in other amplitudes, not in graviton amplitudes. Yes. So this is the Wilson coefficient. Now, of course, this is just the 3 level thing. In principle, you can compute higher orders and all of that. But as Paolo was mentioning, in certain cases, you can go beyond and you can actually compute the exact result to not just to all orders, non-perturbatively. It's different. You can do that. And for example, in exactly as you said, in type 2, right? So you have the type 2A and the type 2B theories. The type 2B exact result for this coefficient is extremely complicated because it involves the non-perturbative effects I was telling Alessia about, like this e to the minus 1 over GS, the brane instantons. It's super complicated. The type 2A is still exact, but it's much simpler in form. And I believe up to a certain coefficient, like in a different definition, is something like, so in Einstein frame now, because it's the one that we care about, it's something like, let's see, it's so there's a square root of GS because of the Einstein frame, and then there's this term over GS squared because of 3 level string perturbation theory, and then I think here actually there's a 96, which makes it no, wait. Wait. Yes, so there is a 64 here if you normalize it according to some conventions. And then there's a one loop term, which is gs to the 0 because it's 2g minus 2. And this happens to be 2 pi squared over 3. And now this is the one loop result in type 2 and A and type 2b in 10 dimensions. Some exact results are known also below 10D. But fun fact, in type 2a, it is the exact result. So equal sign. Yes.
Sorry, what about the poles of the gamma function? Do they have a physical interpretation?
Yes. No, it's absolutely necessary for consistency, and it's very welcome that they have poles. So you see, gamma functions have like infinite sets of poles, and like equally spaced at integer arguments. Not all integer arguments. And you see, I didn't mention them because this is the low energy physics that doesn't care about it, because I isolated the massless poles. But there are massive poles, which for three-level scattering, they signify resonances in intermediate states exchanged by the scattering. And this gives you this string spectrum in flat spacetime, exactly given by the poles of this guy. Like if you set this equal to a non-positive integer, you see you get back like s is 4 of alpha prime times a positive integer. Yeah, so it's the string spectrum in flat spacetime, exactly as it should be. And the residues at the poles are polynomials in P, which tell you the spin of the exchanged massive particle, which match perfectly again with the string spectrum. Everything fits together. Cool. So this is the exact result. I hope I remembered the normalization that was used by some authors, and there's a reason for it. The reason is that this thing, because it's exact in GS, we can look at all possible values you can take. Turns out there is a minimum value in this particular case, which is non-zero. So of course, this must be at least 0 because of a strict positivity bound of the kind that Anna explained. But there's a unitarity bound which is stronger. Can be numerically determined up to some precision, right? And which was done by a beautiful paper by Andrea Guerrieri, Pedro Vieira, Joao Penedones, and I think that's it. Maybe there's someone else in 2021, I think, or so. And again, this bound is so there are two different bounds. Let me be clear. There are two different bounds. This just happens to be the minimal value of the amplitude. You can determine it analytically, and it's about 0.14 or so. This is the sloppy approximation symbol, up to some numerical approximation. Sorry, numerical approximation symbol. This happens to be the minimum of this, and all the other values are allowed. Cool. Now, there is a bootstrap bound, a non-perturbative bootstrap bound, numerically determined up to some precision, for this alpha in type 2 maximal supergravity in 10 dimensions. And it's about, well, so the minimum value from the bootstrap now is roughly, guess what? 0.14. These are completely independent calculations, mind you, completely independent. This has absolutely nothing to do with string theory at all. It's just about if a UV completion is unitary, causal, crossing symmetric, and all that. This must be true up to some relatively small numerical error. I don't know what to tell you. I mean, it's a beautiful result, in my opinion. The point is that it's not just that the string of aqua cover are consistent, because we know they are, but they seem to cover all of them somehow. I mean, this is of course a very small piece. But please let me not oversell this result. It's a small piece of the story. There are other hints of this type, but we are far from oh yeah, that's the only, it covers everything, absolutely everything. But it could have gone otherwise, and it didn't. And there are similar results in other dimensions. And I mean, it's an ongoing, relatively recent research topic. So I don't want to oversell. 10. Yes, in maximal 10D supergravity. I wouldn't say that. The question is if there are other allowed values of alpha in any possible UV completion of type 2 mass maximal supergravity. That string theory doesn't cover. And the answer up to numerical accuracy, as far as I know, seems to be no. It covers everything. Could have gone otherwise and it didn't. This could have been like 75, but it's not. Me neither. No, there's no. There's no input. This is a purely bootstrap calculation. It doesn't assume anything about the UV completion. Nothing at all. Just the basic principles of physics. Unitarity, causality, crossing, all that. Yes. No. This range covers the whole range of allowed values. Because this is not a precise value. I mean, it is a precise value given GS. So given the point. This is a point in moduli space of type 2 supergravity, if you want to be precise. But so the values covered in the moduli space are the whole range. The overlap is there. And we can discuss later. It's fine. I really want to get the last half an hour to the juiciest part, which is the high energy stuff, energy business. Okay. So, any further questions? Okay, good. Let's go. But actually, I basically laid almost all of the groundwork. Sorry, what? Okie dokie. Okay, so high energy. High energy stuff. And UV IR mixing. So of course we're gonna, I tried to pick the most interesting aspects for me that could have been covered with what I presented here. So what does it mean to go high energy? Well, now we have a tool. We have this amplitude here. This is a 3-level amplitude so far. So let's push to high energy. I mean, there's no reason why it shouldn't be valid at high energies because now the coupling is just a constant. It doesn't, it's not affected by the dimensional analysis running that tells us that, the theory would become strongly coupled or something. So the two things, high energy and small coupling, can be parametrically separated here. So the interesting regime for what I'm going to present here is the so-called hard scattering regime or fixed angle regime. You know how many seminars I've seen of people like writing angel instead of angle? I was like, I really cannot mess this up. So this regime fixes the scattering angle in this scattering process, right? Fixes the angle, and essentially the regime is that S and T are large. Let me fix MS. Well, let me fix alpha prime equal to 1. Actually, equal to 4. Let's put it equal to 4. Yes. Why 4? Because it cancels the 4 in the amplitude. I think that should be the right choice for what I'm going to write. And then S over T is fixed to some, it's a function of the angle. So we fix the angle to an order 1 value in this limit. Okay. So basically you aim and you shoot super hard. That's the point. Now, the Virasoro-Shapiro reduced amplitude and stripped of all the kinematical factors and so on, happens to have a cool behavior in the high energy. If you do I mean, it's a Stirling approximation more or less. Now there is so in this limit, let me not specify what the conditions are. Those are the conditions. There is a prefactor that I don't care about, powers, and so like if you take the log, it's subleading. That's what I mean. And then you have something like e to the minus string units, so everything is dimensionless. S log s plus t log t plus u log u. Right? So it's super soft, like very soft. So the UV doesn't actually explode and do crazy stuff. It actually goes super nicely. Intuitively, because if you scatter strings, they're like they can touch at like very small regions, so it's nice and soft. Is it too soft maybe? Because like for instance in gap, the local field theories, there are lower bounds on how fast it can decrease, and it's not s, it's like root s. So it kind of, I mean, on one hand, it seems to be too soft. On the other hand, it's too soft for something that is like a field theory, but this is not field theory, so who cares, right? Nevertheless, it's worth checking out if you can extrapolate this behavior absolutely all the way, right? How can we check this? So this is at 3 level. So how can we check loops? So to check loops, we would have to compute like higher genera, right? And it's a insanely technically difficult task. But the hard regime simplifies things a lot, as was shown by Gross and Mende and Oguri in the late 80s. So we have this kind of behavior we have had it for a while. So the loops in this regime tell us that up to these prefactors that are log subleading, as I said, up to these prefactors, basically the amplitude at a genus G is, again, up to these prefactors, the amplitude at 3 level, so the Virasoro-Shapiro or graviton Virasoro-Shapiro amplitude, to the 1 over G plus 1, roughly, turns out. Which means that, you see, if this is soft, this is less soft, a bit less soft. So for any given genus, everything is soft. But if you resum everything, maybe the actual behavior is different, because at large enough genus, you start comparing different loop orders. You see what I'm saying? So there seems to be a potential competition between the parametrics. The weak coupling regime and the high energy regime could potentially actually not be completely separate after all. So what is the condition here? Let's say we compare G equals 0 with G equal 1. What do we get? Well, we get the A3 level. Well, let me forget about these logs again. You take double logs and it's subleading. You get something roughly, you get e to the minus s here, 3 level. And you want to compare it with the one loop, which will be e to the minus s over 2, times an extra factor of the string coupling square, because it's higher genus. The one loop. So when is this, when is this comparison, up to when is it valid? So we get like, if you solve the equation, you get that root s is roughly, but not numerically, but roughly in terms of the logs that I neglected, is going to be ms. I wanna put it log square root log 1 over gs squared. So this seems to be an estimate, at least an estimate perhaps, of the lambda strong coupling of the quantum gravity theory, right? The scale I hinted at yesterday. And you see that, well, you don't because I didn't give you the calculation, but it's actually indeed much less than the species scale I defined, because this guy is actually, if you do the calculation, is ms log 1 over gs squared. And all of these are also much less than the Planck scale, which is ms over a power of gs. So you see power log square root of log. The scales arrange exactly as we predicted from effective field theory, even more so, even parametrically separating. And again, it could have been otherwise, but it isn't. That's the theme of these lectures somehow. So this is an estimate. So, okay, what can we say beyond the scale then? We cannot trust that. So the true high energy regime is, I heard that. Somehow we need to take care of all them loops. And to take care of them, we need to do some sort of resummation. Now, 100% of interesting interacting perturbation series are divergent with zero radius of convergence, but some of them are Borel resummable, and you can use various techniques to accelerate convergence and so on. And Auguri and Mende in 1999 or something really performed a really detailed Borel resummation which estimates the behavior of this. You can actually check roughly to get the right qualitative form of the result by doing some saddle point analysis in the genus. You can get the right rough scaling. The bottom line is that after this Borel resummation, or at least an estimate of the Borel resummation, because there are some things relating to the phases of the prefactors which were carefully analyzed still. You get a behavior that is not e to the minus s, but rather root s, the one that, remember the bound I told you about. Turns out it is satisfied after all, but non-trivially and non-obligatorily, I would say, because it was a field theory bound anyway. But the point is that there are some logs upstairs, downstairs, depends on the precise asymptotics relating S and G and GS. But there are some logs, but the point is that the root is there. And you can extract this exponent by doing a double log plot if you measure the cross section or whatever. So you can go tell your experimentalist friends, like, oh, hey, this is the super mega high energy thing that should be valid at least by Planck. At least by Planck, we should see this kind of thing. I suppose that this is something we could tell our experimentalist friends to build a galaxy-sized accelerator. Hey, it's not my fault gravity is weak. Tell that to the man upstairs. So this is the thing, right? And this is a beautiful result in my opinion, which has been known since the late 80s. So this seems to be a universal UV behavior. Yeah, I set it equal to a constant. Yes. Yes, I set it equal to, like, in string units. We work in string units. So everything is in, or 4, yes. Yeah. But of course you can just restore it easily. And there is a function of the angle, but it's an order 1 number anyway. Cool. So this is the story. And I mean, this is already amazing because it tells us that somehow string theory is local enough to be consistent with causality and everything, as was shown actually by Paolo and some collaborators in relating to some other aspects of causality. And yet it's not a field theory. So like it avoids the consistency issues of field theory, but then it also remains within the physical principles we know and love. So it's a very, very delicate margin here. Basically no margin, I would say. All right, so can we learn something else from this? Actually, yes, and this is the last thing I'm going to say. Something related to UV-IR mixing. Maybe the second to last thing I'm going to say. No, last thing I'm going to say. I already mentioned some other thing about the vacuum energy, which is again a hint of UV-IR mixing, because we said that it depends only on the scale of the lightest massive states, not the heavy states. Anyway, so what can we learn from this? So something pretty cool. I think I mentioned at least yesterday in the beginning that there's some suggestive picture where, like, if you scatter things hard enough, eventually you form big black holes, right? So this should be valid unless like up to when strings start forming black holes. So if the string is too energetic, strings are too energetic, they should start forming black holes. Now, what is the smallest black hole that makes sense to talk about in an effective field theory? As a minimum radius. So let's say up to square root of s equal, again, parametrically, the mass of the minimal black hole. Now, what is the minimal black hole? This is also called the black hole threshold, by the way, the expected parametric scale at which you start forming black holes. So the black hole threshold is given by when the radius is the UV cutoff. Otherwise, it makes no sense to talk about black holes as effective field theory objects. And this is just ms to the -1 in our case. Here, in the here and now. So this is just like ms 3 minus d and Planck 2 minus d. It's just the standard Schwarzschild formula. It's nothing fancy, except in natural units. But remember what this was. This was like ms d minus 2 over gs squared. So this is just ms over gs squared, which is much bigger than this. So it makes it, we are actually exploring the strongly coupled regime before the black hole threshold. We can do that. So this is the black hole threshold. Should be valid up to here. And then actual black hole formation should kick in. Right? So this is the, we have our square root s, the black hole threshold, and we are here, right? This is stringy physics. And then here we have the UV cutoff, and here we have EFT. I mean, of course, this covers everything, but you know what I mean. Now, what should happen here? This should be what's called the classicalized regime, as Giedvali says, for example, where you produce black holes. And the amplitude here is supposed to look like e to the minus entropy of the black holes. In the 2 to 2 scattering, if you only scatter like an order one number of things, you don't have enough degeneracy to compensate for the entropy suppression of the virtual black holes that you form in the middle. And or if you will, black holes that evaporates to gravitons or whatever. What is this? Well, the Bekenstein-Young entropy, which is reliable in this regime because the black holes are still much bigger than Planck size. So the Bekenstein-Young formula, despite EFT corrections, is still reliable because the first term is Planckian suppressed, not EFT suppressed. That's extremely important. So in this regime, this formula is reliable. And if you compute it in terms of the mass, it gives us this particular thing, which for d at least 4, remember the mantra, at least for d because gravitons exist, blah, 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 this is always bigger than 1, which is beyond any kind of field theory spectrum you can have in terms of density of states and so on. And yet, in the case of strings, these guys you can check explicitly, they match. The amplitudes match at square root of s equals black hole threshold. They match, the parametrics match. So it's a really nice hint that indeed string theory starts producing black holes and classicalizes back to the IR. Right? And finally, like you can reproduce the same result, exactly the same result in a completely independent way. Instead of scattering them at very high energies and then matching with the expected amplitudes, you can look at the degeneracy of string states at very excited string states. So you can also match this with the degeneracy which for string states, I couldn't compute it, but details are in the notes. Finally, someone saying. So there is an asymptotic behavior, which again has subleading factors, and then there is this m over ms times a constant. This is one of the summaries I put, like the notes contain little summaries. And at the end, there is a summary of summaries. So you just, if you're really lazy, you can just look at that. And this matches with e to the s black hole, which is the density of states, black hole states. Again, at m of the string state equals the black hole threshold parametrically. Again, didn't have to. It does. Two independent ways. So it's a really nice hint. And again, the UV-IR mixing is not just at this black hole formation level, it's also in the vacuum energy, because we saw that the free level is completely zero. So at weak coupling, the vacuum energy is dominated by the one loop thing. And you would say naively that the one loop thing is dominated by the cutoff of the EFT. This is what happens in EFT. The heavy states contribute. But somehow, even though it has an infinite tower of states, the vacuum energy is just dominated by the lightest of them, which is just the string scale. It's not like a sum over things that gives you the species scale or anything. It's just the string scale. And this happens also if you have other dominant scales like the Kaluza-Klein scale and so on. It really is UV-IR mixed, and it has a lot of properties that relate different scales. Like for instance, that paper by Stephen Abel I mentioned, by other people in the room, which relates like masses of scalar fields, for instance, the Higgs, if any, and the vacuum energy density relates them in ways that you would not expect. Like naively, in a random EFT, you just get random parameters. But the space of things you get from string theory is extremely constrained in ways that look fine-tuned from the naive EFT perspective. And this is what leads to, ideas from the Swampland program and so on. Yes, so thank you. I'm done.